Thanks for inviting me. It's my pleasure to meet you, especially the students here. Uh, and thank you for accommodating me after the school hours. Things are crazy for us right now for our scheduling. I'm Iftekhar Jaim. I'm originally from Bangladesh, but have been living in states since 2011. And I came here to do my master's and PhD. And immediately after PhD, I started working for NASA, and still I'm there. Excuse me. And I work with many defense agencies directly under them or in collaborating with them for with U.S. Army, Navy, their projects. So today I saw your topic for cars. I got a little bit excited because my undergraduate was in mechanical engineering. Uh, so I literally opened the car engine, disassembled it, and assembled it back and ran it. Many years, like in 2006, 2007. I don't know how old you are, guys, but it's quite a bit while ago. And then we had many coursework that how car works and how the safety things happens. So that was then. But when I was doing my PhD, I also worked on aluminum material and some other materials, which are lightweight materials. So although it was not related to car, it was for Air Force. So their planes that they make are also made of aluminum because it's lightweight. And US Navy ships, naval ships, and their electrical wiring they make. So you know that in Navy, if you can reduce the weight, your fuel cost will be less. Not cost. They don't care about cost. I mean, you can go farther. So it means that you have more times of operation. So it's important. So that's when I worked again on aluminum and other things and other metals. So when your teacher sent me this list, I said, oh, yeah, that makes sense. And also, I helped many other groups on energy materials. So you know that EV, electric vehicle, and all those things that we talk about based on battery system. And since we are in mechanical, I was in mechanical in undergrad, so I also know about nuclear power and many other power plant things. So so if I wish to explain all things, it will go for a long time. So in my PhD program, I did basically on condensed matter physics related topic and some metallurgy. I will not introduce further myself. I will rather take questions from you. And please go ahead because time is limited. Thank you.
Yeah, absolutely, Gabriella. You can feel free to unmute yourself and ask your question.
All right. Hello. I was wondering if you do anything about like what materials were the safest or most efficient for like different types of airbags.
Mm-hmm. So I honestly did not work with airbags, but what I can tell you that these things are in many cases are sort of trade secret. So the companies make these products years after years after years research, and they either do patent, but in many cases they do keep as a secret so others cannot use. But I can tell you some fundamentals what they consider, because fundamentals are known. What it is not known exactly what materials they're using, they're not going to tell us. So the fundamental is that you need something that does not explode when the air is plunged into the system. So that means plasticity of the material. So it can be like your chewing gum, you can expand it, but you are not going to break it. The other thing is that it should not fail, because airbag is supposed to save a person. So it needs to go through very systematic studies that if suppose the car hits from the front, from the side, no matter which direction it hits the car, the airbag works properly. So these are studied at many different government organizations. One is NTSB, I guess, National Transportation Bureau and Safety. And there is another one, I forgot, it's basically for motor vehicle. That one is broad. So they check these things before giving certification to use for any company. Now, although airbag is now quite a bit of mature technology, but from time to time in the newspapers, you might see that there are some lawsuits against some companies who try to save money or made some mistakes. So on those materials, it's basically polymer. Definitely it is polymer. And the way the airbag is said that it can take impact force because the air that comes in is very fast. So most likely they have some sort of cylinder inside a car or somewhere where the air is compressed. I forgot exactly, but it is something like that, plunger, and when it hits a certain momentum into the car, so it within microseconds or milliseconds, not microseconds, or milliseconds, it gives the response that it needs to open the plug for air, and it just opens up and gives the impact. There are other things so the most important thing, it should not tear up. It should come up within millisecond sort of impact, so the person does not lose consciousness or get hit hard. Yeah, that's your answer. Actually, there is not exact answer, and I'm pretty sure no one is going to tell you even they know it.
Yeah, that's fine. That makes sense. Thank you.
Go ahead.
I'm not exactly sure how to phrase it, but like, how do you think like cars and like, or just technology, like space or like anything like that, how do you think like materials and how they're used will like develop in the future?
Yeah, so the material science is sort of the thing that comes later on in any design. So there is a famous example in New York, I guess this is many years ago, like when material science was taken very seriously, like 60, 70 years ago. It's a very famous photo that they built a very big bridge, like suspension bridge, or sort of California, San Francisco Bay Area type bridge. And it broke like this, literally, on the middle. It was like this, and it was very new because they did not listen to material scientists. So that's one of the things that came, the striking example that why you need material scientists. So every design is customized. Like if you have an engine, it's running, suppose at 1200 degrees. I don't know exact temperature right now because I read a long time, but you have combustion. So combustion is pretty hot. Diesel or petrol or gasoline is pretty hot. So suppose if you have combustion, so it's heating. So you know that metal expands with temperature, right? So think about if you start your car, the engine is like this, and you're running, the engine is like that. It's not going to work very well. But it happens. Expansion thing happens. So you need materials which can withstand high temperature. So then the material science comes. How can you make a high temperature material? Then there are other issues. So you have lubrication inside the system of the car, right? So it's rotating everything, camshaft, rotor, or your powertrain. So they're not only getting hot while rotation, they also need smooth running lubrication. So then if you have, suppose, oil on your clothing or on your table, you get stains, right? So in car, you cannot get things stuck because once you get stain or something, it accumulates and your movement will be under trouble. So on that case, you need to add over that high temperature how the fluid will pass easily over the surface. So it's called hydrophilic or hydrophobic based on the application. Then you are having this thing. Now you bought a car, you heard some company, I'm not going to tell the name, it's a new company and they have a lot of market share, but their doors don't open during winter. So the reason is that the people think it's a software, it's a battery. No, a car is a car at the end. So if you don't plan those things, you get a lot of surprise when you sell the product. And fortunately, car industry is pretty old. It's almost 100 years by now. The Ford, I guess, is more than 100 years. So the fundamental things, unless a software engineer or web designer starts making car, is pretty good. Uh, so materials like in aeroplane, suppose that the one that project that I was working in during my PhD was related to aluminum material. Aluminum is lightweight material. That's why that is used in the aeroplanes. Now, over the time, everyone is using aluminum, suppose in war fighter. The question is that if everyone is using the same material, then how can you beat your enemy, right? I mean, everyone is using so that's when the question comes, how you can improve further properties of aluminum so it has the same properties with less weight. So it's a very stepwise thing, like a cooking. Like if you wish to learn cooking, you don't learn Indian cooking or some sophisticated Italian cooking at first. You learn how to make ramen noodles, and then you learn how to boil egg, and step by step it happened for me. I'm a very good cook, but it took several years to go through that process. Then you become a good cook. Materials, we said this is a materials recipe. Literally in our offices we use what is the recipe. So it's like a very good cooking. So it has many steps based on the customer, based on your taste, or based on the environment. The food changes, and it's the same story about material science.
Thank you.
No problem. Any more questions, or I go to the script?
Well, it was one that I asked on the Google form, but I'm curious, like, how much math is involved in your job?
Okay, so in general, if any scientist or engineer is good in mathematics, now there is a little bit confusion, I guess I also had when I was in high school or in undergraduate, that I need to know a lot of mathematics. It might have been useful like 30-40 years ago because there was not that many softwares and other things to do. So you definitely need to understand what you are doing. But the whole idea that a living calculator or living person who can just solve things, those era have gone by, honestly, because you have so many softwares to do that. But you need to understand, otherwise you cannot interpret the result. So what we do, we know the principle, we know what sort of results to expect, and if someone tells us, yes, we can solve it. But if you know that there are softwares like MATLAB and Mathematica, if you write an equation, it's going to solve the whole thing for you. Especially if you put any college mathematics, it's nothing for it nowadays. It will plot every data that you can expect. So my personal suggestion would be that if you wish to, get into science or engineering, try to understand what exactly you get out of that mathematics. I don't know what you read, but if you suppose doing calculus, suppose related to this class, like you have equations of acceleration and the car, right? So car is moving. So and you are presenting the impact force, suppose from speed change, half mv square 1 by final minus half mv square initial, that sort of equation to get the impact force. So so in this case, what you can think that with the less the time, the impact is higher, right? So in that case, you need to think that, okay, if I create a function in a software, there are many softwares. You can use Python, those are free programs, and you plot differently, and you can see that how the impact force can change based on reckless driving. Like I can drive at 45 to 45. Here is the 45, now I can work 95. So what impact force can come over me based on those things? So these are important. The understanding the relationship between parameters. Solving math on hand after undergraduates, I don't think that's a big deal anymore. Any question from anyone or?
Thank you. That was insightful hearing how the application of mathematics is used at the career level, I think. And all the concepts you covered are concepts that they're currently going over, which I'm sure you figured as well too with car safety. Rowan and Yuna, do you have any questions yet before we move on to the list of questions?
No, I came in to kind of just listen. I don't necessarily have any questions.
Yeah, same.
Sorry,
Okay.
there's a dog.
No, that's fine. There are a lot of questions standing in front of me. Okay, so based on the question, and rather than going 1, 2, 3, 4, I will give a sort of summary that can be much more impactful than the questions are. So I'm only one person. There are many people who work at NASA. Believe me, there are a lot more people you think of. There are almost 8,000 employees in our center alone at Goddard Space Flight Center. It's in Maryland. And for you, the closest one will be Jet Propulsion Lab near Caltech, and another is Ames Research Lab in Silicon Valley, close to Virginia. We work with them too sometime. So out of the 8,000, I think we have, I forgot the exact number, maybe 1,600 PhDs inside, 1,500, 1,600 PhDs inside. They might be postdoc, they might be senior scientists, they might be Nobel laureate. Actually, one Nobel laureate works in the building I work sometimes. So it's a broad range. That's what I'm trying to tell. I'm there. There's a Nobel laureate in the same floor, two floors above. Sometimes he works over there. So it's a very wild environment. Now, they actually give jobs to many different types of people, not only scientists and engineers. Like they have professional photographers, web editors, like the beautiful animations that you see. We don't do that. I mean, we are not skilled on that. So they bring people from many different perspectives. They have a lot of project management people who have nothing to do with engineering, because government gives billions and billions of dollar contracts here and there. So you need to manage the money and human resource management. Then from education level, you can actually even start at high school as an intern. So I definitely encourage all of you, if you are interested, to check which branch. So they have many different offices all over the United States. So the closest one for you will be either JPL or Jet Propulsion Lab or Ames Research Lab. And different centers have different specialties because it's a government agency. So they try to make sure that distribution of the money is proper. So they don't do the same thing everywhere. So yeah, if you think of that, you can even think of starting at high school as a summer intern or something like that. Afterwards, in undergraduates, they also take during summer, and even people don't know it, during undergraduate, you can actually start a career at NASA. You don't need to wait until PhD. So the way it works is that suppose you do well in the summer, so they'll take a lot of interns every year. I mean, this year they did online, but in other years, they used to take a lot of interns. So out of those interns who do well, they might call them next time. So suppose next summer. And then if they like, and there are sometimes openings are happening because the US population, I mean, federal government, there are a lot of retirements happening. So there is always openings, not at that level, but I mean, even at the bottom level, there are a lot of openings. So you start over there in suppose in the first year or second year. If they like you, they might even call you to work sometimes spring semester or fall semester. It happened to people. Eventually, if you get along with the system and if there is opening at their level, even before graduating, you can become a sort of government employee part-time. And once you graduate from your bachelor's, you get it. Now, even if you are bachelor's, that's not a problem, because when you do masters or PhD, they have different levels. So that's the point I'm trying to make. You don't wait until you get PhD or something. Okay, that's difficult actually at that level to get in. So suppose you are doing research in PhD or in masters, you can do all of your research in a facility inside NASA. It's not only NASA. Department of Energy has many labs. Department of Defense, Army, Navy, they have all sorts of labs. So you can start working there, and they will pay you a stipend, and then you, if they like you, and if there is an opening, it's not just about liking, they need an opening, then you can might be a permanent employee. And I am not a permanent employee, let me be honest, and let not be pretend. I'm a contractor. So the way it works in NASA, like I guess 70% of the NASA engineers are under contract. So it's not like a good or bad. You cannot say, oh, contract versus government is not the thing to classify, because we have many different levels. Those people who become civil servant, they are going to stay there lifetime if they wish. I mean, until 65 or something like that. Contracts, we do a lot of scientific stuff, which flexible things. So you have a certain project, I have expertise, so it's coming for suppose next 2 years, next 5 years. So you are chosen and you stay there. Now, many things can happen after 5 years. If you wish, you stay maybe in another project if there is availability. Otherwise, you leave. So I'm in sort of positions, but generally, once you start working, making relationship with people, professional relationship, and if you can deliver the things, there is no reason for people to tell you you leave and I'm taking another one. So that's one of the reasons that you see that people work for a long time and people cannot get in from outside in any government agencies. So what I am trying to tell you after saying all these things, that don't be discouraged, whatever major you take in your later life, to apply in not only NASA, in any other scientific organizations, because you always need people from accounting, management. I mean, you cannot run an office with just a bunch of space scientists. It's not going to happen, right? Okay. And then let me check. Someone asked me about satellites. Yeah, I work on some satellite stuff, but not on the mass program, like keeping the balance. So those things are done by aeronautic engineers, and those are very difficult calculations, because I was a mechanical engineer, and those like center of mass, because when the structure becomes three-dimensional and a lot of features come, yeah, the stability of a system, you need to redistribute the mass. So I remember in undergraduate, I guess, yeah, we had that sort of problem. You have many different type of mass, how we're going to redistribute it. Otherwise, it will just start spinning and lose out of orbit in case of satellite. Because you need to keep the equilibrium to get the proper motion of rotation. Otherwise, it will fall off this way or that way. And in one case, actually, this sort of thing happened in China, sent some sort of a spacecraft which was rotating, and it fell off a few years ago, and people were scared that if it hits on the ground. Fortunately, it went to in the ocean. So yeah, that's very important thing to calculate. What types of materials are used in cars? So in materials, if you think about the cars, in the outside, many are using aluminum. It's one of the things. It's not pure aluminum, because pure aluminum can get oxidized very fast. So if it is outside and it is under rain, it's going to corrode. So they do coating with different alloy. So they use other metals mixed with it and roll it and do some other processing, and then they paint it. Paint is just not for color, it's actually to protect the surface from water and moisture, other things. And for inside, they use like plastic and those new nice things inside, but they all have to go through fire safety and other environmental testing. So if any crash happens, you don't die because of the leather in your car. So you cannot just put any types of leather or wood. Like, it's not exactly wood, they use some composite and looks like wood thing.
I have a quick question
Sure.
going off of that. Now that you're talking about the materials off of cars, some of the students are researching right now about crumple zones and a little bit about impulse, which you talked a little bit about at the beginning.
Hmm.
Do you have any insight onto how materials are used for crumple zones in cars?
I'm not getting what exactly crumple zone you're meaning.
In the front of the car where it will deform at the front of the car.
Okay. Sorry. We call generally. We have another term for that. Yes. So
Oh.
that one is called. Yeah. I get it. It's the bumper. We used to tell this thing. Okay. Yeah, so that one is designed in such a way that if you collapse anytime, the metal will shrink like this. So the whole idea is that it's kept in such a way it's little bit fragile, because if it is too hard, you will get the shock. So it's like a spring. So when we used to do calculation, we used to make sort of simplification that this is the material. This has this flexibility, so we used to calculate as a spring in our engineering. So it does several things. So it takes the impact, and it also gives you time to get the airbag working, because if you get the impact immediately, you cannot. It's difficult for the airbag even to launch. So these materials are ductile materials, so they can deform. So when a material deforms, it absorbs the shock energy. And that can be done by some material modification and mechanical design modifications. Like if you stack something like this, so when it crashes, it will have some place to deform. So like you see in the bumpers, like this sort of thing. So there's some spacing. So if it deforms, it goes here, it goes there. It's empty space. So they keep some space empty so it can change. Like if someone is angry, you don't get very close, right? Because it's moving. So it's leave him alone. So that's the principle in materials. Leave those parts alone so they can crack, break. You might take $1,000 or $2,000 to replace that one, but that's nothing compared with your life or medical bills. So that's the idea.
Yeah, thank you very much for elaborating on that one.
Okay, so I see one interesting question. What kind of materials are space technologies made out of? Yeah, that's a good question, because when we are on this Earth, we don't deal with many problems because we have ozone sphere. This multiple sphere, right? Stratosphere. So they take out UV light and many atomic oxygen. So that's why we can breathe on Earth. We cannot go outside without space mask. For materials, the same thing happens. So actually, I helped in one group that was launched at International Space Station. So it's orbiting right now outside. So they were making some sort of thermal management system. So, but they could not quantify that how the material is impacting their behavior testing on Earth. So I helped them to figure that out, what material characteristics changed. If I could not figure that out, they could not launch it, because you don't just send things on space to test. So it was very critical. So the environment is different. Now there are different levels, like the satellites that goes have different height. So the mission that goes to moon has a different types of materials than the things satellites are moving, because their atmosphere is different. The thermal energy that they go through on other places, that's different. The solar radiation they get are different. So the solar radiation is a very big problem, because it is very powerful. And so you need to take care of that. That's why I was saying that like thermal management is one issue, because it's either very cold, either very hot. So the materials goes frequent hot and summer and winter. Like right now in our area, what's happening that in the morning is like 44 Fahrenheit. During day is close to 80. Within just 4 hours, and it's just making everyone very uncomfortable. So the same thing happens with materials. It's called thermal cycling. There is a limit how many times you can do this thing. So these materials go through those testings, either changing thickness or coating or design, how to take the shielding. And it also depends on the application, like the semiconductor materials are used as sensors on this earth and on space. But if you are on space, then you have to make sure that radiation does not damage semiconductor materials. In terms of metal, oxygen can attack. So it's very application based. And at NASA and other places, what they do, they have controlled environment. So instead of testing in normal atmosphere, they have a box where it's either very hot or very cold or have lack of oxygen or more oxygen. So these are called environmental testing. So they go through this and then decide whether it's space technology or not. And that's actually the most distinguishing feature of the things that we do, that we make space quality stuff. And it's very difficult to pass because you cannot just open a book or go in Google and see, let me see what Japan is doing or what Toyota. I mean, suppose other companies are doing, because no one did this thing other than us. So it's up to us to build that technology, and that distinguishes us over there. I was good at math when I was in high school. That's true. Okay, so when you are talking about math, I already talked a little bit, but I personally recommend, there is a website called Khan Academy. I guess that many of you already know. So it's not about for school kids alone. Believe me, even a few months ago during Corona, I was practicing SQL. That's a program. It's a very easy program, relatively easy program for data analysis. So the first thing came in my mind, I will check with Khan Academy, because that's for a preliminary thing. I can go to higher level later on. So I still sometimes check small things here and there. And I think that's a very good effort, like so many free lectures on mathematics. So if you have conceptual problem, go to khanacademy.com, and they are totally free. I guess mostly free. Yeah. So if you wish to see the lectures, that will help you. How safety features are implemented in rockets? I think I told you a little bit. Yeah. So they do testing again and again and simulate the situations. And they always have a plan if something fails. So we always have a backup plan. That's why we are very famous for having backup plan, that even if someone dies out of 3 persons who are going to space, how they will handle everything is planned over there. But still failure happens, as you know, because out of 20,000 electronics, if 1 or 2 fails, the whole mission can fail. And there might be weather issue. Few happen due to weather issue and many other technical issues. Okay, SpaceX questions. Okay, SpaceX question. This is good to know, because there's a lot of media hype that people misinterpret. Actually, one journalist from a big television outlet wrote a very wrong information about after the launch of SpaceX. He wrote that private companies are saving when government is failing, something like that. And I commented on his LinkedIn post that you are totally wrong, because you don't know how NASA works. So the way it is happening, like, the government is trying to give contracts out, and it always happened. Like Lockheed Martin, Northrop Grumman, then there are other big aerospace companies, Raytheon. They always get government contracts. So the way it works, the government gives the money and it gives some goals. Now, if they have to put report, and government also helps. It's called private government partnership. So the way SpaceX work is that NASA's always helped them and guided them how to get through that. And they also bring a lot of money and brain into the game. So it was a partnership. It's not like they are taking over NASA or NASA is taking over them. Because the money from US Congress or Senate comes to NASA, and NASA takes the ideas from Lockheed Martin, Northrop Grumman, SpaceX. And whoever gives the idea with the least cost and with some new ideas, get chosen in a fair process. And then once they're chosen, they are guided through the process because it's for everyone for this country. So yeah, it's a sort of, you can think that it's new Lockheed Martin or sort of, I mean, in a sort of sense. I'm not comparing because they're very different, but still it's a sort of, but they have a very good media strategy, which is not present in other defense contractors. So that's why people know about them. How engineers considered using graphene for a materials to use in rocket. I actually, in my PhD thesis, there are some parts of graphene sort of material. So one of the ideas, they think that graphene can be used because it's very strong material. Most probably that's what you heard on the news or in the popular article, is the strongest material. Now the problem with that strongest material is only strongest at multiple nanometer level or maybe maximum micrometer level. And the rocket is like, I don't know how many hundreds of feet tall or how many 6 stories tall. I don't know. I mean, it depends which rocket we are talking about, right? So it's not possible to use carbon material like someone told this spacewalk, like you make a staircase from Earth or rope that you go to space station. There's a science fiction with carbon-like material. In reality, it's not going to happen. But what it happens that in my work that I was working, we mixed graphene sort of material with aluminum, silver, and many other materials. And we got like 30% more strength into the material. So what it means that if for the same application, you can reduce the weight by like 20-30%. So that's how graphene is used. And another carbon material is being used in aeroplanes nowadays. You might have seen in the news that they use lightweight carbon-based material. In Formula One cars, they also use carbon-based material. So there are applications going on, but those are composite. It's not just graphene or carbon material. So they mix with other polymer or other metals. So you get the lightweight. So that's how the graphene or nanotube are going to work. What physics concepts are needed to account to launch a rocket? There are too many because it's, but the main principle is your Newton's third law, according to your textbook. That was the basic principle. So yeah, and the second one is also important, that momentum conversation. So those are like several hundred years ago, but it took a long time. There are so many things. Actually, not a single person can tell you because everyone works in small parts. Someone works with the rocket fuel, someone works with the engine, someone works with that part of engine, how it's going to be heated, how it's going to be cooled. That's for aerospace engineers, material scientists. Physicists generally don't get involved in these things anymore in these days. They work in different things like finding planet, or you have sensors that you wish to find gamma ray, X-ray. Those things physicists work. And aerospace engineers basically are in charge of those things. But as I told you, like if you saw that last SpaceX, they did not have to do anything. It was just like your automatic flight. So it's more related to control system. It's called control engineering. So like so you hear a lot about machine learning. These things are actually done a long time ago, but the terms are not popular. Like if this thing flips this way, what will you do? You emit some gas or something, so it gives particle. So this is called control system with different mechanism. Basically, it takes the data and it decides already if it happens, what will you do? It's a sort of computer program. So that is called guidance system in missile guidance system or rocket. Principles are basically same. And that's one of the things they are trying to do on the car, like autonomous car. It's basically electronics, machine learning, machine vision, computer vision. It's nothing to do with mechanical. The engine will be the same. I mean, there is no change in the engine over there.
I have a quick question.
Sure.
gone over this one yet. You talked about so far how engineers all work on teams, right?
Yeah.
Working to build a rocket. I'm wondering, though, whether it's within the team or all the teams working together when they're starting a brand new project. What's the process like to design something new?
Yeah, so although I'm at a very junior level, but I have some glimpse how it works because I work with very senior people. So it comes, as you know, that it's a sort of process that starts at the Congress or president, that they decide whether we're going to moon or Mars, or whether we'll look into telescope more or go man mission or something like that. So it starts from over there. Then it goes to, I guess, National Space Council. Right now it's directed by Vice President Mike Pence. So they have this from NASA headquarters, Air Force, and some other very big people, not Nobel laureates because they're aeronautics, but they're sort of that level people over there. And they said, yes, this is the good project to go. And then the headquarters decides that we have like, I forgot how many centers, 14, 15 centers, maybe 17 centers. So which center is good for that? So they choose a center like GSFC, Goddard Space Flight Center, or Jet Propulsion Lab, that, okay, you guys are going to do this thing. Now, meanwhile, since you are going to suspend a rocket or something, for many years, people on the desk decide what is achievable and what is not achievable. So they come with the discussion. These things takes years and years. And then they set the goal. We are here, now we to improve here. Now, how long is the mission? So is it worth it? Does it make sense financially? How much risk is involved? That's why I'm saying you need all sorts of people, risk management people, whether it's going to work or not, because you don't wish to lose money in sending stuff which doesn't work. And then all those decisions, then it comes to, from those big people come to, there are many divisions. So those divisions heads get that this project is going and they wish to do this thing. Can we do it? Then it goes to different branches. And the branch managers check that whether they have the capacity or the people to do it, or whether it's achievable or not. And then the branch managers decide, okay, we don't have these things, but we wish to do these things. Then what to do? Then they give publicly open contract on their website. These are the things we wish to do. We need grant proposals. Million of very small thing. The project will cost $1 million. You'll get it if you can show. Then they give the project, like I worked on the project. At first, they give money for 6 months to see how things are going. It's called phase 1 project. Then if it looks promising, then they give the phase 2, like for several years. Then if it goes well, and sometimes it goes well because it's research, there is no guarantee that it's going to work. If it goes well, then it gets selected. And they also have competitions from many different companies, as I told, not only SpaceX or Lockheed Martin, many small companies, because that's their specialty. Then they call them and we do the competition. If we win, we get selected. Like before Corona, I got selected. One of my stuff is going to be a part of satellite, but it was not like they told me and I made it. There was a sort of competition from different companies who got involved. And once I showed this is the best thing I can give you with your criteria, then they select it. So it's a sort of fair process. And that's why it takes a very long time to come up with this idea. And some companies might take a lot of bragging that they're doing faster, but there is also a risk if you do things fast, because when a government agency tries to do, they wish to make things that safe because it's public's money. There is no private investor or eccentric people coming up with ideas. It's a government money, taxpayers' money. So they wish to make sure that that money is not wasted. And there are some accidents on space, as you know, Challenger and others. So some astronauts died. I mean, that's not something that anyone wants. So we have very strict safety protocol and other things. And when many people retire or come out of NASA and they join groups, then they drive from the same knowledge they derived from NASA to those companies, because those companies never work in space. And NASA is 60 years old. So they bring their expertise in private companies, definitely higher compensation over there, but nothing wrong with that. So that's how the whole process goes. And it also is sometimes changes. Suppose if US economy is bad, it happened many times, the budget contracts in government agencies. So we are susceptible to the global, US economy. So that's another point.
Yeah, thank you very much.
Thanks. Okay, let me see. Okay, someone questioned how do you start thinking or design process when developing satellites. So as a continuation of this, generally the satellite technology is matured. Now, why would you send a satellite? That's the question. Sometimes it is for fundamental science, like Einstein gave a theory, suppose 100 years ago, and we are still not sure about that. They have projects like that. So you make very specific type of satellite just to find that one. And there was a NASA once got Nobel Prize some years ago. I was a school student, I guess, then, or undergrad maybe, I forgot. So that they found background radiation. It's called background radiation. So there was a theory and here and there, but there is no map of it. So there is a very famous picture. If you ever Google it, background radiation map, you will see a big map. And that map was built by the people who knew that they're going to find that thing. So they made the instruments. I was lucky, actually. Some of the colleagues actually were part of that mission, like that background radiation map, and they made the instruments that got Nobel Prize. And I also had the opportunity to work with the people who worked with the Hubble telescope missions. In our offices, it's like sort of museum because we have to keep things. So if you walk through, you can see, oh, this is because you make a lot of stuff, keep ready. If anything goes wrong, you put them, you don't delay the mission. So this is from this mission is sitting over there here. So it's really interesting that you're literally working in a lab and it's a sort of museum too, because you have so many things from so many different missions left over. Yeah, so like now we are talking a lot about the climate change. So you need the satellites which can detect the climate change through optical system, or for NOAA that they give you the pictures of the hurricane, which or the California fire. Think about it. These things came from satellites, the pictures. So you focus, what is your goal, then make the scientific strategy, and then you give the contract, or they also do research at home. I mean, their own research. So everyone works together, and then they find out whether it's useful. I mean, whether they're going to launch it or not. So what safety features are implemented in rockets? I mean, you try to make it as safe as possible, but the recent one you might have seen like 6 months ago or something like that, that I guess Boeing also tried, SpaceX also did. One became successful, another didn't. So what they do is that now, since the astronauts' lives are the most important thing, no matter how rockets are expensive or important, so they made a system like a fighter jet system. You know, in the movies you see that the missile is coming and the fighter presses a button from F-16 and just have the whole seat goes up and with a parachute and then drop that thing. So that sort of idea was in the head of, I mean, in our head for a long time. So they made a system, I guess, in SpaceX and Boeing both, that if anything really bad goes, I mean, if things don't work and it's going to be devastated, so they can take out the capsule of the astronauts so they don't die. I mean, they can land safely. I think that's a very big progress. I mean, no matter what we say, that's a very big progress, because now hopefully no one will die. Yeah, actually it was tested in a very unfortunate way, because I think Boeing was trying to do and it did not work well and they had to take out something like that. I mean, it's like a year ago it happened. I think what is the hardest part of our job? Actually, it's not possible to define what's the hardest part. I can tell you what I'm doing right now. It was making us crazy, not me, many of us. So what happened during the coronavirus, you know, everything was closed, and we are not private companies who will tell that coronavirus doesn't exist, so you have to come in the office. We don't do that. So we had to go. So they are very, very nice about this thing. They try to make sure we don't get COVID-19 every day. So we could not come in office in the last for certain period, almost 4 months, from March to, I guess, July or August, something like that. What happened that if you keep the scientific instrument switched off for a long time, they don't act normal. It's like not having parents in a house for 4 months. Okay, so that's exactly happened. So it's a very scientific thing, because when instruments run, they have a specific condition they maintain. But if it is off, they get the moisture or get fatigued. I mean, a lot of things happen. Now we are trying to go back where we were like 6 months ago, and different instruments are giving different troubles. It's not only us, it's all over any scientific organization. If it is switched off for 6 months or 4 months, it's a huge struggle to come back. And that's why I was working like crazy, because already we did not work for several months, things have piled up. On the top of that, the instruments are acting bizarre. And when you use like 5-10 instruments, then you don't know who is the culprit. Like you have 10 students and one is making noise and the teacher is writing, and who is making noise? Everyone is silent. So that's more trouble for the instruments, because you cannot tell that I'm going to give everyone bad grade because they don't care. Now that's actually really hard to come back. Now we're working very hard, and I was working something 9-10 hours on site nowadays. Yeah, so I guess I cover pretty much everything. Now if you have some questions, I can answer a few minutes and then I have to leave. Yeah.
Yes, thank you so much. You answered so many of the questions. I'll leave it to the students to see if they came up with any more right now.
Yeah.
Do you
That's
guys
fine.
have other questions? I think we covered them all. What do you guys think? Yes.
Yeah, so I just wish to tell that I personally believe that access to information will be to everyone. So even I'm talking to your teacher actually right now. Even later on, if you need information or something about any scientific stuff, feel free to contact me. I mean, I'm giving my permission to contact me directly, because what is happening in the United States, we don't have enough engineers and scientists. And the way the economy worked in the last 20-30 years is now a very different economy. It's not like people are learning and staying. Now people are returning. So we are getting a lot of competitions from outside. And American supremacy in technology is actually relatively much less right now. And it's creating a lot of trouble in the whole world. Believe me, it's a very personal thing, but I work with a lot of defense people. I can tell you, I can sense this problem. So I encourage you to come in science and engineering, definitely. And the good thing about science and engineering is that you can always change your track. You wish to get into management, people will love you to see in management. You wish to get an MBA schools are waiting. Actually, many business professors have science and engineering degrees, especially engineering degrees, business professors in top ranked schools. So if you spend your 4 years, do something that gives a tangible benefit, and you also learn and contribute. And if you wish to become a CEO later on, yeah, go ahead. I mean, no one is stopping you. Yeah, that's what I feel sometimes. Take some hard skills in your career.
That's fantastic. Thank you for encouraging for that. And then one question that students were asking too was for students that may already be considering, wow, a career at NASA sounds great. What kind of advice would you give to them on how they could get there?
Yeah, I think I already told that. Yeah, the easiest way to get there is starting through internship. You start internship, you apply. I mean, you don't lose any money. It's a government agency. You can apply always. But the other tactics I can tell you is that you focus on something like take part in competitive things like math Olympiad or physics Olympiad, chemistry Olympiad. Distinguish yourself. That's the point. Like the questions that you were asking me, believe me, if I go in restaurant, I never tell if they're not known that I work at NASA. I tell I just work engineering and sort of stuff. Because if I tell immediately, I'll be asked for 5 top questions that I already know they're going to ask me. So I just don't tell them. But what I'm trying to say you, the competition is huge to get in. So you need to distinguish yourself that you are good, not only enthusiastic. Enthusiasm is good. You should be enthusiastic to work at NASA or anywhere. But you also have to show that you have credentials, because that's how if they get 100 applications, how they're going to say, I like to work? No. So you do some competitive things or take part in science projects. The other thing I can tell you, I don't know whether you have universities nearby your place. Universities also take high school students or even middle school students, if they are good enough, in their research things, to mentor them during summer or other times. So in that case, the National Science Foundation, NSF, actually gives sometimes conditions when they give grants to the professors, that how it's going to impact the society. So to get the grant, everyone tries to tell, hey, I'm going to take one undergraduate from minority or something, suppose, and also from high school, at least one during my project. So although they are not that, they're trying to get that money, but the government also knows that, but it has a good impact on you because you have the opening over there. Because to meet the grants rules, they have to take someone from high school or undergraduate or something like that. So especially for females, there is a lot of movement going on in United States, organizations and universities to take them in science and engineering. And there are a lot of fellowships. You have no idea how many are actually waiting for you. So even you start working with the science group, and that's also important to know that whether you are really interested or not, because people have fascination from television movies or series that they think they can solve the problem within 3 hours. Science is not that fun, believe me. It's a lot of hard work. So once you test it, you can know that whether you are suitable for it or not. If you are suitable, then, and all these experiences will distinguish you from other students when they apply at NASA or any other organization in your whole life, that you were active from your high school.
Absolutely. Thank you so much. And I'd love to add on to the students, the university that you were speaking of. We do have an engineering university nearby. So Cal Poly San Luis Obispo is a great engineering school to network with for you students that are listening right now and maybe watching this video later. And we have the Society of Women Engineers nearby. That do summer programs just like you're talking about. They do outreach all the time. Yeah, so they'd probably be a good resource for them.
Yeah, the other small thing I'll add, that is like the one that I think you were talking about, Wise Women in Science and Engineering or something like that. There are many professional societies based on your interest. Like you like robotics, you can look for professional societies in robotics in your area or something, and then look for student members at high school, because that's one of the things that professional societies are for mentoring, taking them into that track. So even at high school, you can check, and their memberships are mostly free. Because you are high school, I mean, who's going to take money from high school? Even at undergrad, they're on many times free. So look in the resources in your area that's available and join them. I mean, you will get news, good, nice magazines where you will get the resources that you need to follow through. So it will be a sort of mentorship, and you can contact them because everyone has different interests. If you ask me about biology, I know nothing about biology. Yeah, so if you're interested, you join a sort of that group, and that distinguishes you for all over your life.
Great. Thank you so much. You've answered so many of our questions today and even more. We really appreciate your time with us today.
Yeah, I'm very happy to talk with you. It never tires me talking with young people, because I think that's our responsibility beyond our office hours to reach people, because not everyone is lucky to be with scientists. I mean, it's not everyone's have that opportunity beyond some big cities.
Yeah, absolutely. Well, I think that was all of our questions.
Yeah, I think it's, I think.
Thank you so much. And
thank you so much.
To unmute yourselves or thank our guests as well. We appreciate your time so much. Thank you.
Yeah, and I will send you the link. You can review, and if you wish, you can tell your students, or if you wish to join in on that lecture, is feel free to just join in. Okay.
Okay.